So in this lecture we are going to talk about multi-stage compressors. Okay, so what does multi-stage compressors mean? Multi-stage compressor means we are going to achieve the required pressure. Okay, previously what we had to do, what is the work of a compressor? We need to compress the air which we had, okay, which we had available with us. We need to compress that and we need to achieve a certain pressure. Okay, we need to achieve a certain pressure by compressing that air. Okay, that was our main aim, or that is the main aim of a compressor. Now in multi-stage compressor, what we can do, we will achieve that same amount of pressure in stages. Now in some stages there will be 2 or 3 compressors, okay, which will help us to achieve that same pressure, but with the help of 2 or 3 compressors. Okay, so the question in the last class we have, or in the last lecture we have learned about single stage compressors. What was the work of single stage compressors? Single stage compressors used to compress it in a single stroke. Okay, it used to compress it in a single stroke and it used to raise the pressure of that same air. Okay, now what is going to happen, we are going to achieve it by different stages. Now the question is there any requirement of multi-stage compressors, or we can easily do it with single stage compressor? Is there really any necessity of this multi-stage compressor, or it is just a waste of time? Okay, so we are going to see this now. So first of all, if you remember, this is going to be the PV diagram of the single stage compressor. Okay, this is going to be the PV diagram of single stage compressor with clearance volume. Okay, and if you remember, we had found out the volumetric efficiency expression. Okay, this is the expression which we have derived. Okay, the volumetric efficiency. Now in this volumetric efficiency, the term was 1 minus C into P2 by P1 to the power 1 by N minus 1. Okay, now from here what is going to be the P2 by P1? P2 by P1 is nothing but the pressure ratio. Pressure ratio is what? P2 by P1. P2 is what? It is going to be the required pressure. Okay, required pressure. That means at what pressure we need the air now. Okay, and P1 is what? P1 is nothing but whatever the initial pressure was there. So after the compression, whatever the pressure it has achieved divided by the initial pressure is going to give us the pressure ratio. Okay, this was the pressure ratio. So in the last class we had again seen something. Okay, we had seen that if we increase the C means what? C means what? C means is the clearance ratio. C means the clearance ratio. Okay, C is the clearance ratio. So in the last class we have seen that if we increase the C, your efficiency was decreasing. Okay, if you increase the C, your efficiency was decreasing. Similarly, we have also found out that if P1 was fixed and P2 increases, then also efficiency used to decrease. Okay, then also efficiency used to decrease. Now P2 is increasing, P1 is fixed means what? P2 increasing and P1 is fixed means what? Your pressure ratio is increasing. Okay, and if pressure, that means what? From this, what you can say, if the pressure ratio is increasing, then the efficiency is going to decrease always. Okay, efficiency pressure ratio increases means your efficiency also decreases. Now let us suppose at some point Rp is going to achieve a value of 1 by C plus 1 whole to the power n. Let us suppose somewhere while it is increasing, the pressure ratio is increasing. Okay, so after increasing at some point it has reached the, that means what? Your pressure ratio P1 is always fixed. That means you are keeping increasing the P2. Okay, you are keeping increasing the P2. Your P2 is increasing. Okay, so suppose at some point this pressure ratio is going to achieve a value of 1 plus C plus 1 whole to the power n. Now if you put this value here, what is going to be there? Okay, in place of P2 by P1 you are going to put this value. What is this value? 1 by C plus 1 whole to the power n. Okay, and there is another 1 by n minus 1. Okay, this would be your expression now. Okay, now if you can see this n to the power 1 by n, this n is going to get cancelled out. So that means what is remaining here? Remaining here would be 1 by C plus 1 minus 1. Okay, so this is plus 1 and this is minus 1. 1 is getting cancelled. Okay, after this is getting cancelled, this is C into 1 by C. So C and C is also getting cancelled means what? 1 minus 1 is going to be 0. Okay, that means what? if somehow your pressure ratio reaches a value of 1 by C plus 1 to the power n, okay, that means what? If pressure ratio is increasing means what? Your pressure 1 is always going to be constant. This is your available pressure. But this is your requirement. P2 is your requirement. Now we do not know what is going to be a requirement. It may increase sometime, it may decrease sometime, which is going to depend upon the situation. Okay, in some situation, suppose we have air at 1 bar. In some situation, we may need 10 bar pressure air, or in some situation we may need 8 bar pressure air. Okay, so that means what? If you are increasing this, and at somehow after increasing this your pressure ratio is achieving this value, your efficiency is going to get 0. Okay, that means what? Efficiency, this efficiency is 0 means what? Your swept volume will be there, but the air, okay, efficiency, volumetric efficiency is what? The volume of air that has been sucked in divided by the swept volume. That means efficiency 0 means this is going to get 0 at some point. Okay, at some point this is going to get 0. That means you will pull the piston, but the air will not get into the cylinder. Okay, the air will not get into the cylinder if you keep increasing the final pressure. Okay, final pressure if you keep increasing, that means what? At some point we need another compressor. Okay, at some point we are getting efficiency 0. That means what? We need to do that in stages now. Okay, we need to do the compression in stages now. Okay, because this is the maximum pressure ratio which we can go to. Okay, if this achieves this value, this is going to be 0. So at some point we need the multi-stage compressor. So you can say that multi-stage compressors are always necessary for us. Okay, and another thing is that if you apply intercooling, okay, intercooling between the stages of compressors, then your work required by the compressor is going to get decreased. Okay, so what did I say? I said that between the stages, if we use intercooling, okay, that means what? If we are compressing, okay, if we are compressing, suppose we need to go to 8 bar. Okay, suppose now I am compressing it to 2 bar. Okay, from 1 bar to 2 bar, I have increased the pressure up to 2 bar. So I am cooling down the pressurized air now. The pressurized air is at 2 bar. Now I am cooling it. Okay, cooling it isobarically. Okay, that means keeping the pressure constant, I am now cooling it. Then after cooling up to some point, then after we are going to compress it again to some other extent. Okay, if we do it like this, our work required by the compressor is going to get decreased. So how it is going to get decreased, we are going to see in the next board. Okay, now we are going to talk about two-stage compressors with intercooling. Okay, so as we have told earlier, if we apply intercooling in between the stages of two different compressions, then the work that has been required by the compressor is going to get lesser. So how it is going to get lesser, we will see now. Okay, so this is going to be the basic layout. This is going to be the basic layout for two-stage compressors. Okay, two-stage compressors with intercooling. So this is what? At point 1 there will be delivery of air. Okay, there is air which is getting delivered at point 1. So after compressed, C1 is compressor 1 and C2 is going to be our second compressor. Okay, so after getting compressed at compressor 1, it is going out at point 2. Okay, so after reaching point 2, it is now, after getting compressing, its volume is getting compressed, and its pressure is also getting increased. Okay, so that means what? The temperature is going to get increased now. Now what will happen? Through intercooling we are going to attain a temperature at T2. Okay, so after that we are going to compress it again in compressor 2, and we are going to reach at point 3. But the question is, the intercooling would be at what extent? Okay, or by intercooling at what temperature we are going to go? Okay, so we must remember that after intercooling, whenever the air is getting at a point of 2 dash, okay, that 2 dash, the temperature at point 2 dash must be having the same temperature as the same of the delivery air. Okay, must have the same temperature as that of the delivery air. Okay, so that means what is happening? After intercooling, it is reaching the temperature same as that of the initial temperature. Okay, and after that getting compressed in compressor 2, it is reaching point 3. Okay, now let us see what is going to be a PV diagram. Okay, so for better understanding, we are taking one compressor with the clearance, without the clearance volume. Okay, so first of all, what will happen? After suction stroke, it is going to reach at point 1. Okay, so after this is the suction stroke and it is reaching point 1. Okay, after that what is happening? After that it is going to get compressed and reaching point 2. So this is going to be a polytropic process. So that means what? We are going to compress it like this up to point 2. So at this point we are going to achieve point 2. That means after the first compression. Now what is happening? We are going to intercool this. Okay, now after intercooling at constant pressure. Okay, this must be at constant pressure. Okay, intercooling must be at constant pressure. That means what? Keeping the pressure constant, we are going to cool this. Okay, now keeping the pressure constant, if we cool this, what is going to happen? The volume is going to get decreased. Okay, if you cool the air, okay, keeping the pressure constant, the volume is going to, so at constant pressure it is going to get cooled. Okay, so at this point it is reaching a point of 2 dash. It is reaching a point of 2 dash. Okay, so 2 dash means what? Then after that, after reaching 2 dash, what happens? The another compression is going to take place and it is going to reach at point 3. So from here polytropically another compression will take place and it will reach point 3. Okay, it will reach at point 3. Okay, so this is going to be the PV diagram. This is going to be the, similarly if you write what is going to be the TS diagram, so first of all what is going to happen? The compression is going to happen. Okay, so after compression what is going to be there? This is going to be the scenario. The temperature is going to get increased. Okay, so after that what will happen? At constant pressure you are going to come at the same temperature at that of previous one. Okay, so this is going to be 1, this is going to be 2, this is going to be your 2 dash. Okay, so after that what is going to be there? You are again going to compress it. Okay, you are again going to compress it isentropically and it is going to reach at point 3. Okay, so this would be the TS diagram. Okay, and this is going to be the PV diagram. Now as we have told earlier, intercooling, after intercooling the work that is required by the compressor is going to get decreased. So how can we know that? Suppose we had to go in a single compressor. Suppose this is going to be a pressure of 8 bar. Okay, suppose this is a pressure of 8 bar and suppose this is a pressure of 1 bar. Now we are achieving this in 2 different stages. Okay, suppose for a moment we had to compress this in a single stage only. Okay, so this would have been our point 3. Okay, this is point 3. So let us take this as 3 dash. 3 dash is what? If we had compressed it in single stage, then we would have reached a point of 3 dash. Okay, now as we have told earlier, in open system how can we find out the total work that is required or the total work interaction? By plotting or by projecting that total curve into the pressure axis for open system. Okay, for closed system we will project that in volume axis, but in open system we are going to project this in pressure axis. Okay, so if you would have gone through this single stage, this total area would have come into your picture and this total area would have been your work done. Okay, for your single stage. Now as we are adding intercooling in between the two single stage or two stages, okay, 2 stages of compressor, now what is going to be the total work done? It is going to be only this area. This much amount of area would be there. Okay, so obviously the area that is being bounded by, suppose this is 0 point and this is suppose 0.4. Okay, so the area that is being bounded by 0, 1, 3 dash and 4 is going to be our work that has been required by single stage. Okay, but the area that has been bounded by 0, 1, 2, 2 dash and 3, 2, 2 dash and 3, that is the area that is that has been achieved after we have used the multi-stage or 2-stage compressors. Okay, so we can see that, we can say that this much amount is extra, this much amount of area is extra for single acting or single stage compressor. Okay, this much area is extra for single stage. So this is going to be, so this much work is what? This much work is what? This much work is nothing but work saved by intercooling. By intercooling, that means what? This much amount of area or this much amount of work has been saved by intercooling. Okay, so we can now say that it has been proved that if we use intercooling between the stages of multi-stage compressors, then whatever the work that has been required by us or required by the compressor is going to get decreased. Okay, so work required in multi-stage compressor with intercooling always requires lesser work. Okay, so now we are going to see what is going to be the total work that is required by the compressors in case of multi-stage compressors. Okay, so as we know, from 1 to 2 the compression has been done by one compressor, that is compressor 1, and from 2 dash to 3 the compression has been again done by another compression, that is compressor 2. Okay, so two compressor has helped us in compressing this from pressure 1 to pressure 3. Okay, so what is the total work input that is required by the compressor is nothing but this work input must be that work that has been given by or given to compressor 1 and the work that has been given to compressor 2. Okay, so both these things will be the total work that has been input. Okay, so we have found out in the single stage compressor. Okay, so 1 to 2 is going to be one single stage compressor and 2 dash to 3 is going to be another single stage compressor. Both these together will be a multi-stage compressor. So as we have found out that for a single stage compressor, what is going to be the total input required is nothing but if the polytropic is given, okay, and polytropic index is given, then it is going to be n by n minus 1 ma r t1, then the pressure ratio of the first one, that is p2 by p1. Okay, I am writing it for compressor 1. Okay, for compressor 1 the initial conditions we write ma r t1. For this the initial condition is t1. Okay, then the pressure ratio of the first one p2 by p1 to the power n minus 1 by n minus 1. Okay, so this is going to be the work that is required by the first compressor. Okay, and for the second compressor it would be n by n minus 1, and now there would be the initial conditions for the second compressor. Okay, now this is going to be the second compression 2 dash to 3. Now what is the initial conditions for compressor second compressor? It is in 2 dash. Okay, so this would be nothing but ma into r into t2 dash. Now ma is going to be constant. Okay, ma is not going to change because after that compressor it is again going passing through the intercooler and reaching the inlet of the second compressor. Okay, so whatever the mass of air is there, it is not going to change, but the initial conditions are going to change. So ma into r into t2 dash, okay, multiplied by what? The pressure ratio. Now the second pressure ratio, what is going to be the second pressure ratio? Pressure ratio is going to be nothing but p3 by p into p2 dash. Okay, so the second pressure ratio is p3 by p2 dash, okay, to the power n minus 1 by n minus 1. This is going to be the work that is required by the second compressor. Okay, this is by first compressor and this is by second compressor. Okay, now if you see you can as we have told earlier that through intercooling we are going to reach at point we are going to make the temperature at point T2 dash as same as that of temperature at point 1. Okay, while we are drawing the multi-stage compressor layout or two-stage compressor layout, we have said that after passing the intercooling, whatever the temperature, up to what temperature we need to cool it down must be equal to that the same of the inlet or delivery air. Okay, so obviously this is the point where delivery air is there. Okay, and we need to make the temperature of T2 dash same as that of T1. Okay, or the temperature at that point T2 dash must be same as that of temperature at point 1. Okay, so we can write that T1 must be equal to T2 dash. Okay, T1 must be equal to T2 dash, and another thing we can write P2 is now going to be equal to what? P2 dash, because from 2 to 2 dash it is coming at constant pressure. Okay, it is coming at constant pressure. So from here now you can see that T1 is going to be equal to what? T1 is going to be equal to T2 dash. So in place of T2 dash you can now write it as T1. Okay, in place of T2 dash you can now write it as T1. Okay, and in place of P2 dash you can write P2. Okay, in place of P2 dash you can write P2. Okay, so now if you see you are going to see that from both these terms. Okay, this is going to be one term and this is going to be another term. So from these terms n by n minus 1 ma r t1, n by n minus 1 ma r t1 is going to be common. Okay, these are going to be common. So if you take this common, what will be the remaining things? N by n minus 1 ma into r into t2 dash. Okay, n by n minus 1 ma into r into t2 dash. Okay, n into r into t2 dash. So now if you see you can write P2 T1 you are taking as common. Okay, now what is the remaining thing that is inside the bracket? That is nothing but P2 by P1. P2 by P1 to the power n minus 1 by n minus 1. Okay, and another thing that is remaining is this part. Okay, so it would be what? Plus P3 by P2. P3 by P2 n minus 1 by n minus 1. Okay, so this is going to be the case now. Okay, now you can take this as x. Okay, n minus 1 by n is going to be equal to x. Suppose, okay, we are taking this x so that it is easier for us to differentiate this. So why we are going to differentiate this? Because in multi-stage compressor we need to find what is going to be the conditions if we need minimum work input. Okay, compressor is a device which consumes work. Okay, so to increase the efficiency, the work that has been given by input must be minimum. Okay, and to find the minimum work conditions, okay, or to give to for the compressor to consume minimum work, what must be the conditions that we require? For finding out these conditions, we need to derive this. Okay, we need to derive this, and the derivation of this must be equal to 0. Okay, so up to now you can say that after finding x, the final equation would be x into 1 by x. N minus 1 by n is going to be equal to x. So n by n minus 1 is going to be 1 by x. So you can say ma into r T1 by x, okay, multiplied by P2 by P1 to the power x plus P3 by P2 to the power x minus 2. There is 1 minus 1, there is 1 minus 1. So after that it will reach minus 2. Okay, so in the next board we are going to derive this. Okay, so and after the derivation is going to be equal to 0. Okay, we are equating the derivation with 0. So after that we are going to find some conditions. Okay, following which we are going to find out what are the conditions for minimum work that is going to be required by the compressor to compress it from pressure 1 to pressure 3. Okay, so now we are going to find what would be the minimum work condition. Okay, to get the minimum work condition we need to derive this. Okay, so first of all, to get the minimum work condition we need to, so this is the expression which we have found in the last board. This is going to be the expression for work input, okay, in two-stage compressor. So if you derive this work input, but with respect to what? Okay, with respect to what we need to derive this. Okay, now if this is the conditions, okay, you will be given what is pressure 1, that is at what pressure you are going to get the air, and the final pressure also will be given. Okay, finally at what, or the desired pressure where you need to up to which you need to compress the air, that thing also will be given. Now if you are given polytropic index, n is given, so x is what? X is nothing but n minus 1 by n. So if n is given, your x is also known. Okay, so from this expression we can say x is the variable here, but it is not the case. Okay, so n is given, so x would be, again x would be the constant. Okay, x will gain a constant value. Mass of the air would be known to you, r would be known to you, and the initial condition temperature would be known to you. Okay, so what is the thing that is not known to us is going to be the P2 is what? P2 is nothing but the pressure at the pressure after the first stage. Okay, P2 is going to be the pressure after the first stage. So we are going from 1 to 3, but we do not know up to where should be the first, up to where should be the first compression up to. Okay, that means after the first compression up to what pressure we need to go, we do not know this. Okay, and after that up to reach point 3 or to reach pressure 3, from what point we need to start, that also we do not know for getting the minimum work input. Okay, so obviously from 1 to 2 this pressure is not known to us. So if we find that if we find out at what pressure we need to compress with the first compressor, and after that for the second compressor what should be the initial conditions, or from what point it should start the second compression, If that is known to us, we can easily find out what is going to be the minimum work input conditions. Okay, so here only variable thing is the pressure at point 2. Okay, that means that what pressure we need to compress after the first compressor is working. Okay, so if you derive this with respect to P2, then you can find out the work input conditions. Okay, so this is good, and you must equate it with 0. Okay, because for minimum conditions, for minimum, if this is minimum, that is derivation should be equal to 0. Okay, so after that, what you need to find, you need to derive this with respect to, P2. Okay, so from this expression, what is this thing is going to be constant, because x is constant, ma is constant, x is constant, ma constant, r constant, and t1 constant. So since it is constant, it will come out. Okay, since it is constant, it will come out of the bracket, and after that what would be done? Now from here P2, now you can write this. Okay, P2 by P1 whole to the power x. You can write this as P2 power x and P1 power x. Okay, you can easily write this. Now from these two, P1 to the power x is common. Okay, P1 is the initial condition, pressure at initial condition. So P1 to the power x is going to be common. Okay, so P1 to the power x is going to be as it is, common and constant also. P1 to the power x is going to be constant. So as it is constant, it will remain as it is. Now what thing will get derivated? This thing. P2 power x is going to get derivated. Okay, so if P to the power x is going to get derivated, what will be the condition? X to the power P2 power x minus 1. Okay, this will be the condition. We all know that if there is a condition x to the power n, derivation of x to the power n, okay, with respect to x, what it is going to be? N into x to the power n minus 1. Okay, where n was constant, x was variable. Similarly here, this is variable and this is constant. So x will come out and p to the power x minus 1. Okay, plus for the second case, now also you can write it as p3 to the power x, and you can also write it as p2 to the power x. Okay, so p2 to the power, from here p3 to the power x is going to be common, so we will take it outside. P3 to the power x is going to be common, so we are going to take it outside. And this p2 to the power x is what? P2 to the power x, you can write it as p2 to the power minus x. Okay, or you can rewrite it as, what? You can rewrite it as p3 to the power x into p2 to the power minus x, because it was p3 by p2 whole to the power x, and there was one minus 2. Okay, so after writing this, p3 to the power x is going to come outside, because p3 to the power x is constant here. Okay, so if you want to do this, if you are p2 to the power minus x, that means what? Minus x would come outside. Okay, and the remaining thing is what? P2 to the power minus x is already there, and minus 1 would be there. Okay, and there was a minus 2. Minus 2 is going to be constant, so it is going to be 0. Okay, now from here, and this is total thing would be equal to 0. Okay, total thing would be equal to 0. Now you can see, we can erase this minus. Okay, we can erase this minus and we can put this minus here. Okay, now from this multiplied by this is going to be equal to 0. Okay, this multiplied by this is going to be equal to 0. So we can consider, we can take that this part is constant. Okay, this part is constant. That means what? Mass of air is constant, r is also constant, t1 is constant, x is constant. So this part is not going. So this multiplied by this is going to be equal to 0. That means what? Either this part is going to be 0 or this part is going to be 0. Okay, so this is having all the constant values, so this will not have the 0 value. Okay, so this part is going to have the 0 value. Okay, 0 value means this part is going to be 0. This part is not going to be 0 because this is constant value. Okay, so if you write this, what it is going to be? X into p to the power x minus 1 by p1 to the power x minus p3 to the power x multiplied by x into p2 to the power minus x minus 1, and 0 is there, equal to 0. Okay, this is the final condition we are getting. Okay, this is the final condition we are getting. Now this minus this is going to be equal to 0. That means what? This is equal to this. Okay, one thing minus another thing is going to be 0, that means what? This thing and this thing must be equal. So either of writing equal to 0, in we can put an equal sign here. Okay, we can put an equal sign, and there was minus sign. After going to other side of the equal, it is going to be get positive. Okay, so we have converted that minus sign into equal sign. Okay, so this is going to be the final condition. Now from here what you can do, what you can see, there is one x and there is another x. These both x is going to get cancelled out. Okay, so for this, the remaining thing what we can do is p2 to the power x minus 1. We will bring all the p2s at one side, because p2 is unknown. P2 is unknown. We need to find where should we take the p2. Okay, so we need to find to find the work output. We need to find what is going to be the value of p2, or at what pressure we need to compress with the first compressor. Okay, so we'll take all the p2s in one side and we'll take all the others in the other side. Okay, so here it is p2 to the power x minus 1, and there is a 1 p2 that is multiplied, okay, in multiplication relationship with power minus x minus 1. So this will come here in the denominator, p2 to the power minus x minus 1, and there is going to be what? p1 to the power x into p3 to the power x is going to be there. Okay, p1 to the power x and p3 to the power x is going to be here. Okay, now if you simplify this, what is going to be there? Okay, now p2 to the power this and p2 to the power this, that means what? This would be what? Nothing but p2 to the power x minus 1 minus of minus x minus 1. Okay, this is going to be the case. Okay, and there it would be p1 to the power x and p3 to the power x. Okay, so now you can see if you erase the bracket sign. Okay, if you erase the bracket sign, what would it be? It would be nothing but plus x, because it in front of this bracket there was a minus, so this would be plus x and this would be plus 1. Okay, this would be plus x and this would be plus 1 after erasing this bracket. So plus 1 and minus 1 is going to get cancelled. Okay, plus 1 and minus 1 is going to get cancelled, and there is one x plus x. So x plus x is going to be 2x. Okay, now in both sides, and in place of p1 to the power x and p3 to the power x, we can write p1 and p2 whole to the power x. Okay, so in both sides it is going to have a pressure of it is going to have a pressure 2x, and this is going to have a power of x. Okay, so you can write this p2 square whole to the power x and p1 p3 whole to the power x. So from both sides you can erase x again. Okay, because if the powers are same, okay, if two terms are, so we can say that if 2 to the power x is going to be equal to 8, okay, then 2 to the power x is going to be 2 to the power 3, then we can set x equal to 3. Okay, okay, so we can write it here, so we can erase the x's here. Okay, after erasing the x's, what it is going to be, so that means what? P square equals to now p1 into p3. Okay, now if you remove the square, it is going to be what? It is going to be root over p1 into p3. Okay, it is going to be root over p1 into p3. That means what? You need to find what is going to be p2. The final condition that we have got is going to be p1 into p3. Okay, p2 is going to be what? Root over p1 into p3. That means what? Whatever the pressure we need to do, okay, whatever the pressure we first we should do, that means whatever the pressure that must be achieved by the first compressor must be the geometric mean of the initial pressure and the final pressure. Okay, that means p2 must be the geometric mean of the initial pressure and the final pressure. Okay, if you find the p2, then it would be easier for you, so that you can find the conditions for minimum work input. Okay, after you find the p2, the work input, find the p2 like this. Okay, or take the geometric mean of the first pressure, or you can say the initial pressure and the final pressure. Then whatever, after finding this p2, then whatever the work that would be required by the compressor would be minimum. Okay, nothing, no work can be minimum than p2, where the second stage, okay, pressure at the second stage is going to be the geometric. Okay, so this was the condition which we have found for minimum work input. Okay, So here we have written P2 is equal to root over P1 into P3. Okay, so we can also write it. If you remove this root over sign, you will need to put a square here. Okay, that means what? P square is equal to P1 by P2. So from here you can write it. From here you can write it that P2 by P1 must be equal to P3 by P2. Okay, you can write it from here. One P2 will remain here and one P2 will be divided by divided. Okay, one P2 will be used to divide P3 by. Okay, so there will be P2 by P1 equals to P3 by P2. That means what? From the same condition, we have found out the condition for minimum work input. From the same condition, we have found out this, that P2 by P1 is equal to P2 by P3. Okay, that means what? That means what? Now, to get the minimum work, okay, to get the minimum work, and there must be one intercooling. Okay, so that means to get the minimum work with perfect intercooling, we need all the pressure ratios in each stages. Okay, pressure ratios in each stages must be same. Okay, so P2, here it is T2, 2 dash, 3 and 1. Okay, so for compressing this, P2 by P1 is the pressure ratio, and for compressing this, P3 by P2 dash is the pressure ratio. Okay, so that means what? To get the minimum work input with perfect intercooling, pressure ratio at all the stages must be same. Okay, pressure ratios at all the stages must be same. Okay, now suppose there are n number of stages. Okay, there is only 2 stages. Now suppose you need to go for n stages. Okay, now you need to go for n stages. Okay, so for n stages, what would it be? The theory would be same. P2 by P1 must be equal to P3 by P2 must be equal to P4 by P3 dot 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 dot. You must go for P to the power n plus 1 by P to the power n, and this must be going to be equal to K. Okay, if you want to go for n stages, okay, if you want to go for n stages, okay, then you need to go for P to the power n plus 1 by P to the power n must be equal to K. That means pressure ratio at each and every stage must be same. Okay, pressure ratio at each and every stage must be same. That means what? From this you can find out that P2 is equal to what? P2 is equal to K into P1 now. Okay, because P2 by P1 is equal to K. Okay, similarly if you want to find P3, P3 is what? P3 is nothing but K into P2. Okay, is equal to what now? P2 is what? P2 is nothing but K into P1. So you can write it as K square into P1. Okay, so similarly what you can find, you are finding for P3. Okay, now if you want to find P to the power n plus 1, the P to the power n plus 1 must be equal to K to the power K into P to the power n. Okay, P to the power n plus 1 should be K into P to the power n. Okay, now P to the power 1. So here you can see P3 is equal to what? K to the power K square into P1. Now here P to the power n minus 1, n plus 1. Okay, now here must be what? It must be K to the power n into this is P1. Okay, because if this is going to be n plus 1, then this is n, because this is 3 and this is going to be 2 and it is multiplied by P1. So if this is going to be n plus 1, the value of n would be 3 is there. Okay, the value of n would be 2. 2 plus 1 must be 3. Okay, so if you want to get, for generalizing this, okay, I am generalizing the conditions. Okay, so P to the power P n plus 1 must be equal to K to the power n into P1. Okay, K to the power n into P1. So from here, if you want to find out what is K, from here if you want to find out what is K, what will you find? P to the power n plus 1 by P1 whole to the power what? Whole to the power 1 by n. This is going to be the condition. That means what? This is going to be what? This is going to be the pressure ratio at each stage. Okay, this is the pressure ratio at each stage. At each stage, this is the pressure ratio. Okay, so pressure ratio is at each stage is going to be the overall pressure ratio to the power 1 by n. Okay, to the power 1 by number of stages. N is what? N is what? N is nothing but the number of stages. Okay, n equals to number of stages. So that means what? P to the power n plus 1 means what? The final pressure which we need to achieve. P to the power n plus 1 is the final pressure which we need to achieve. And P1 is what? P1 is the initial condition of the pressure. So the final condition or the final pressure which we need to achieve divided by the initial pressure is going to be the overall overall pressure ratio. Okay, if we had gone to this pressure, P to the power n plus 1 in a single stage compressor, then this would have been the overall ratio. Now we are going to the same pressure in different n number of stages. We are going to that by n number of stages. Okay, so for going to n number of stages, we need to specify each and every pressure ratio at each and every stage, and each and every to get the minimum work input. Okay, that means for minimum work input into the compressor, each and every pressure ratio must be defined, and each and every pressure ratio must be equal to the overall pressure ratio to the power 1 by number of stages. Okay, so this is going to be the concept for pressure ratio at each stages. Okay, so now we are going to find what is going to be the work input that is required per stage. Okay, per stage. Okay, in multi-stage we are going stage wise. So in each stage, what is going to be the total work input? Okay, so work input per stage. Suppose we are going from 1 to 2. Okay, we are going from 1 to 2. The compression is taking place in 1 to 2. Okay, so for that we have found out the expression in multi-stage compressor itself. Okay, that is what? That is nothing but Ma into R into T1. Okay, Ma into R into T1 to the power P2 by P1 to the power n minus 1 by n minus 1. This was the condition. Okay, so P2 by P1 is the pressure ratio here. Okay, P2 by P1 is the pressure ratio here. Now what you can say, P2 by P1 is the pressure ratio, and for each stage, okay, for each stage after the intercooling has been done, we are reaching the T1 itself. Okay, after each intercooling, when the next thing starts, okay, when the next stage will start, after the next stage is starting, we are again going to write Ma into R into T2 dash, but T2 dash is again going to T21 because we are making the temperature same as that of initial condition. Similarly, if we are going for third stage, okay, if we are going for third stage, we are again making the initial condition for the compression same as that of this. Again, this will be same as that of this. So ultimately, this temperature would be same as that of this temperature. Okay, so if you join this line, this would be an isothermal line. Okay, if you join this line, this would be an isothermal line. Okay, so that means what? You can place T1 here. T1 would be constant for each and every state. If you want to find out, the temperature at T1 would be constant. Okay, now from this, what you can say, the pressure ratio is going to get, pressure ratio is always going to be same. Okay, pressure ratio is always going to be same to get the minimum work input. Okay, so if the pressure ratio is always going to be same, and we have said that the pressure ratio would be having a value called K, then you can write this as K to the power n minus 1 by n minus 1. Okay, so this is going to be your work done per unit stage, per stage. Okay, in each stage you are going to have this much, because for this, for finding out each work at each and everything, this is going to be constant, this is constant, this is also constant, this is also constant, this is also constant. Now for minimum work input, K is also constant. Again, n are also constant, and minus 1 is already there. So this would be in any stage. If you want to find out what is going to be the work input in this stage, this is the formula with T1 only. Okay, if you want to find what is the work input in this stage, this is the formula. Okay, same formula would be there. Okay, if you suppose if you want to find P2 dash and P3 dash, okay, you want to find P2 dash and P3 dash, okay, the compression here, but you don't know what is the pressure at P2 dash and what is the pressure at P2 dash and what is the pressure P dash. There would be no worry, because P2 is here and P1 is here. Okay, now we have found out for minimum work input, P2 by P1 is must be equal to P3 by P2 dash. Okay, so this must be equal. So if you do not know P3 and P2 dash, you P2 and P1 would come into rescue. Okay, so in place of P3 dash by P2, P3 by P2 dash, you can write P1 by P2, because the pressure ratios is going to be constant for minimum work input. Okay, so this is going to be the work that is required per stage. Okay, so what is going to be the work input, total work input now? What is going to be the total work input now? It would be nothing but, so this is in one stage, and there are n number of stages. In one stage it is going to take this much of work input. So in the total, how much it will take? It will take number of stages multiplied by the work that has been taken as input in each stage. Okay, so this would be the formula for total work input. Okay, total number of stages into work done in each stage. Okay, so this is going to be your total work input formula. Okay. Okay, so this is going to be the total work input. Okay, this is going to be the total work input that we require in multi-stage compressors. Okay, now in the last to last board, while we are saying about the pressure ratios, okay, we are saying about the pressure ratios, we have found out in some point that pressure ratio must be equal at each and every stage, and that must be equal to what? Overall pressure ratio. Okay, pressure ratio overall, that means P final by initial, P final by P initial whole to the power 1 by n. Okay, this we have found out. Okay, the pressure ratio must be equal to P final to the power P final by P initial to the power 1 by n. Okay, this would give the pressure ratio. So in this formula, if you replace K by P to the power final by P initial, that means n into in this formula it is n by n minus 1, n by n minus 1, ma into r into T1, and in place of K you are writing this. In place of K, if you are writing this, that means what? Pf by Pi whole to the power n minus 1 by capital N into small n minus 1. Okay, this would be the formula. This would be capital N into small n. Okay, n minus 1, because n by n minus 1 by n was already there. Okay, now if you replace K, there would be 1 by n, 1 by capital N extra in the powers. Okay, so Pf by Pi to the power n minus 1 by capital N into small n minus 1 would give you the formula of total work input. Now what is the benefit of this? What is the benefit of this? If in the question they have given the final pressure, okay, the final pressure where you need to give, okay, suppose this pressure is given and this pressure is given, you don't need to find the initial intermediate pressures. Okay, now you don't need to find the intermediate pressures. Now you can directly put the value of final pressure and you can put the value of initial pressure. Okay, number of stages would be given. So if you put all the things in this equation, then with the help of final pressure and initial pressure only, you can find out what is the scenario here and what is going to be the total work that is required as input. Okay, so up to this our compressor is reciprocating compressor is done.